For this video, we'll have the continuation of multiple integrals, but their applications in inversion of orders and change of coordinate system. So we'll have the first part, the inversion of order. The objectives are to apply the inversion of order in evaluating iterated integrals, and for the second part, we'll have write and evaluate double integrals in polar coordinates. For the inversion of order, it's first with respect to x, right? So let's see that. So you know that this one will be with respect to x, because x is the first term there. Therefore, if that's the case, y is constant. So if y is constant, what is the u? X squared plus y, potentially its power formula. So n is negative 1/2. If y is constant, that means this one would be 0. The differential of u is simply 2x dx. There is a problem, guys. In this case, we don't have an x on top. So that means if we don't have an x on top, this one, let's note this. This is not integrable, so it cannot be integrated. It cannot be integrated with respect to x, y, because no x in the numerator. So, you know na, if there is an x on top, it could be integrable. But, ito yung another note. If it is in the order of dy dx, do you think it would be integrable? If it's in the order of dy dx, yes, because there we don't need a y on top. But if it's in the order of dy dx, what happens is this. If with respect to y, where x is constant, the u will still be the same, x squared plus y. The n would still be the same, negative 1/2. The du would be 0 plus dy, or simply dy, because if x is constant, the whole x squared becomes 0. So if it's in the order of dy dx and not dx dy, it would be integrable. So what happens is we have to know the limits. What are the limits? So what we do here is, let's look at the original limits first, because it's termed inversion of order. So what are the original limits? It's with respect to x first. So here, this is the first limit with respect to x. This is the second set of limits. So with respect to x, x would be 0. X would be square root of 4 minus y. With respect to y, y is 0 and y is equal to 4. So guys, take note of these limits. They are the original limits. What happens is here, we try plotting it from x equals 0, which is this portion. X equals 0 is this. And then x is the square root of 4 minus y is the parabola. Actually, half of the parabola facing downwards. So it's this. Y equals 0 is this one, the horizontal line. Y equals 4 is the horizontal line on top. So let's look at dx dy. It says there dx dy. Look at the square. The square travels along the x first. It travels left and right. And then once it has completed the rectangle would travel up and down to fill out the area. So again, this one is the dx. Then the dy, this one. So the travel of this one would be left and right, the travel of this one would be up and down. So what happens is, since we are changing the order or inverting the order, it's still the same problem, but let's try redrawing the figure. Instead of a horizontally simple element, let's try drawing a vertically simple element. So here, let's rewrite the original limits. The original limits were x equals 0 to x is equal to square root of 4 minus y equals 0, y equals 4. So we know this. What we have to do is we change the limits. So let's rewrite this. That means x squared equals 4 minus y, or y equals 4 minus x squared, right? If we are to rewrite that. So what will be the new limits? That means for the new limits, it has to be y and y, x and x, because we will invert the order. If it's dy first, the y will travel from here, below, up until the top. So below, that's y equals 0. What's the top? It's the parabola. What's the equation of that parabola? That parabola, it should be y down and then y up. Y up, it's y equals 4 minus x squared. Therefore, let's rewrite that. Actually, it's that one. And then, once you have completed the rectangle, first again, it's this one, dy, it travels up and down. And then once it has completed the rectangle now will travel left and right. So the leftmost portion that the rectangle will travel is, leftmost is x equals 0. Rightmost is, again, instead of the equation, because there are two variables. The first are sets of equations. The last are sets of constants. So from x equals 0 up until the rightmost would be x equals 2. So here, up to 2. So if those are the new limits, I could evaluate them. I could evaluate the integral. This one would be from 0 up until 4 minus x squared. This one would be from 0 up to 2. So let's rewrite. So dy dx, we have already inverted the order. Square root of x squared plus y. This is 0. 4 minus x squared, 0 up until 2. So if we are to evaluate this, it's with respect to y, x would be constant, u is equal to x squared plus y, n is negative 1/2, du would be 0 plus dy, or simply dy. It's integrable. So what's the integral of that? Let's do it here. First step, with respect to y. That means we can apply the power rule. Um, 0 up to 4 minus x squared of x squared plus y, negative 1/2 dy. I'm not copying the dx yet, huh? We're just doing the first. And then we were able to prove here from the left that with respect to y, the power rule is applicable. So integrating it becomes from 0 to 4 minus x squared. Let's apply. So the question is, where are we applying these limits? Again, you have just integrated with respect to y, so that means these limits would be applied to letter y, or to the variable y. X squared plus 4 minus x squared minus the square root of x squared plus 0, 2 times the square root of 4 minus square root of x squared. So this is 2 minus x, or simply 4 minus 2x. So guys, this one is the answer for the first set. Now we are integrating with respect to x. So let's write the problem. From 0 to 2 of what? 4 minus 2x dx. So we know that this one is readily integrable. That's just 4x minus x squared from 0 to 2. That's 4 minus 4 minus 0 minus 0. So this one is 8 minus 4. So the final answer is 4. Let's evaluate this. So here, it will be evaluated with respect to, as it is, with respect to x. Therefore, y is to be given as a constant. If it's this case, let u be x squared plus y squared. N is 1/2. Du would be 2x dx. Now, the question is, you have y outside, not x. So that means you cannot supply an x. This one, not integrable with respect to x. But if dy dx, meaning if it's this case, with respect to y, where x is constant, again, the u is x squared plus y squared. The n is still 1/2. The du, x is the constant one now. So it's going to be 2y dy. So look, guys, outside the square root, there is a y. So that means in this case, this one would be integrable. Integrable if the order is dy and then dx. If we are to invert the order, guys, it would be important to know the limits. So the limits will be from, first initial limits are x and x, y and y. Limits would be x equals 2y up to x equals 2, y equals 0 up to y equals 1. So for this case, we should know the how to draw the figure. So x equals 2y. So when x equals 0, y equals 0. When x equals 1, when y equals 1, x equals 2. So that line up until x equals 2. And then y equals 0 up until y equals 1. This is y equals 1. So that means x equals 2y is this line up until x equals 2, y equals 0 up to y equals 1. So it's the lower triangle, because if you draw this, some of you might be asking, which ones do I focus on? Is it the lower or the upper triangle? Look at these limits. It starts from x equals to y. It starts from the line going to the constant. So going to this, to the right. So it's not x equals 0 up to the line. It's line up to x equals 2. So we should know that the figure we are looking at is the lower triangle. Now, for the lower triangle, the order is dx dy. How do you draw dx dy? Dx dy, guys, is, again, this shape. You start with a dx, and then it becomes dy. We would want to have a dy dx. This is dy dx. The square travels along the y first, and then the rectangle travels along the x. So that means we need to have a rectangle that is upright. And then we'll have a square inside. The square would have limits of dy, and then the rectangle would have limit of dx. So since we are inverting the order, we have to set the new limits. The new limits would be, this one has to be y first, and then x. So look at the r square. The square will start from y equals 0 up until the line, because figure to figure, right? This one, what's the equation of this line? That line is x equals 2y, or y equals x over 2. Therefore, this one has to be x over 2. And then the rectangle will travel from constant to constant. The constant, leftmost constant is x equals 0. The rightmost constant is x equals 2. So look at the limits on top. The limits on top were originally um x equals 2y up until x equals 2, y equals 0, y equals 1. It became y equals 0 up to y equals x over 2, x equals 0 up until x equals 2. So let's try solving that. It's the same. This is the original problem. But then we are to rewrite it with new sets of limits. Again, for inversion of order, the problem will not change. The problem will be as it is. But then the order will be inverted. It's dy dx. The limits are, the new sets of limits are y equals 0 up until y equals x over 2, and then 0 up to 2. So again, let's go to the first one. It's with respect to y, where x is constant. So let's rewrite. U is x squared plus y squared. N is 1/2. Du is 2y dy. We already have y. So when we rewrite this, guys, let's just copy the first set of integrals. Y square root of x squared plus y squared dy. You know that from the top, all you need is 2 in here. So let's bring out 1/2. So this is 1/2, and then x squared plus y squared to the 3/2 all over 3/2, coming from 0 to x over 2. So this one outside becomes 1/3. This is x squared plus y squared 3/2 coming from 0 to x over 2. So let's try to evaluate this. That's 1/3. So where will you plug in x over 2 and 0? To the letter y. So x squared plus, so x over 2, that's going to be x squared over 4, 3/2, minus x squared plus 0, 3/2. So this is 1/3. This is going to be 5x squared over 4, the 3/2, minus this one is x squared. This is just x cubed. So 1/3, 5. So this is 5 square root of 5 over 8 x cubed minus x cubed. This one. So we don't need the constants. Let's just bring out first the x cubed. So that means x cubed over 3. The constants would be 5 square root of 5 over 8 minus 1, right? And then if you want to combine this, square root of 5 minus 8 all over 24, and then x cubed. And then what happens is, let's integrate it the second time around, but now it's with respect to y, with respect to x. Now it's with respect to x. So let's rewrite the integral from 0 to 2 of 5 square root of 5 minus 8 all over 24 x cubed dx. We don't need all the constants. We can bring out the constants. X cubed, when you integrate that, that's going to be x to the 4 over 4 coming from 0 to 2. So 5 root 5 minus 8 over 24. This is going to be x squared. 16 over 4 is 4 minus 0. So 5 root 5 minus 8 all over 6. This is your final answer. Okay, so we integrated it first with respect to y. After that, it's with respect to x. With number 3, it's with respect to y and then with respect to x. So let's try for with respect to y. Meaning x would be constant. The original u is 1 plus y cubed and is 1/2. That means du is 3y squared dy. The problem is we don't have a y squared outside. So meaning this one is not integrable. So let's try to invert the order. If it's in the order of dx dy, we have to change the uh, limits. But let's try. If it's in the order of dx dy, it's going to be, the whole thing will be constant. It is integrable with respect to x. We don't have a problem. So meaning we can do integration with respect to x with respect to y. So this is where it gets tricky, as I said. Originally, the limits are square root of x up to 1, x equals 0 up to 1. So we have to draw this. From y equals the square root of x, so it's a parabola opening sideways, up to y equals 1. Let's just say this is y equals 1. And this is y equals the square root of x. And then from x equals 0 up to x equals 1, let's say this is x equals 1. So it's the upper figure. How do I know it's upper? Again, from the parabola upwards. So it's that one. If it's the lower one, it should be y equals 0 up to y equals the square root of x. But since it started from the square root of x going up, it's the upper figure. However, the order was originally dy dx. How does this shape look like? The element would be this one, dy dx. We would want it to be dx dy. So it's horizontally simple. Let's draw the square. So that's dx, and then the yellow would be dy. Let's just write here the intersections. That's 1, 1. All right. So we're finished. We have the same problem, 1 plus y cubed, but then it will now be x and then, x and then y. So the order is dx, dy, meaning x has to be the limits first and then the y. So look at the square figure. The square figure will travel from left to right. So this one, we can rewrite this as x equals y squared. So the square will be from x equals 0 up until x equals y squared. And then now the yellow going up and down will travel from constant to constant. The lowest constant is 0. For y, the highest is 1. So if you are to rewrite this, 0 to 1, 0 to y squared of 1 plus y cubed dx dy. So that's the new problem. Let's try to answer that. 0 to 1 and 0 to y squared of 1 plus y cubed dx dy. So let's go to the first one. With respect to x, where y is constant, the whole thing is constant now. So I can say 1 plus y cubed integral from 0 to y squared of dx, right? The whole thing is constant. 1 plus y cubed x from 0 to y squared. Therefore, this one will then be y squared minus 0, 1 plus y cubed, or basically y squared 1 plus y cubed. And then now, after integrating that, we integrate that with respect to y. From 0 to 1 of y squared 1 plus y cubed dy. So with this, if u is 1 plus y cubed, n is 1 half, du is 3, y squared dy. You already have the y squared that was missing earlier. All we need to do is supply a 3, bring out 1/3. So let's solve this. 1/3, 1 plus y cubed to the 3 halves over 3 halves. From 0 to 1, this becomes 2 over 9. And then 1 plus 1 to the 3 halves minus 1 plus 0 to the 3 halves. This one is 2 to the 3 halves minus 1. 2 to the 3 halves is 2 squared of 2. So 2/9, 2 squared of 2 minus 1. This is your final answer. By the way, in here, I gave some more problems. What happened was, so this one's already solved. You can see in here that y equals x squared, y equals 1. So originally, dy dx. So originally, it's the dotted. And then we changed the order to dx dy. It became the solid rectangle. So it was already provided to you, the drawing in here. So you can evaluate the new limits. The final answers are already given as well. There. And another problem with the old limits and the new limits. You can see in here that the change in limits from dy dx and then the new limits of dx dy. And then the final answers are provided for you to study. For this one, the original limits were y equals x, y equals pi, x is 0, and x equals pi. Okay. So if the original limits or the original order was dy dx, you cannot integrate it. Why? Because you have sine y on top and y at the bottom. So as it is, it's not integrable. But if the order is dx dy, will it be integrable? Yes. Why? Because the whole thing, the sine y all over y, will be constant. You can integrate with respect to x. So that means this one is integrable. So let's check. For the limits, y equals x is a line, y equals pi. Let's just say this is pi. So that's y equals x, that's y equals pi, x equals 0, and x equals pi. So x equals pi, this is x equals 0. So from the figure, y equals x up to y equals pi, you know that it should be the upper triangle that we have to consider. So the original limit is in the order of dy dx. Now we would want it to be dx dy. So the square will travel along the x first, and then, so that means you will have a horizontal rectangle because the x will travel along the square will travel along the x, and then the whole rectangle will travel along the y. So that's dx, and then this is dy. So since we are changing the limits, guys, the Original problem will stay as it is, but then this one becomes dx dy. So the x will travel from 0 up until x equals y, up until the figure, which is the line. And then the rectangle will travel from 0, 0 up until this intersection that is actually pi, pi. So these are the new limits. So with that, let's do our first integration. If it's with respect to x, the whole y is constant. So if we rewrite this, I can bring out sine y over y. This is the new problem, right? So sine y over y, x from 0 to y. So that means sine y over y, y minus 0, right? The y cancels out. You are left with sine of y. Now, we are finished with this. Let's integrate with respect to y. If we are integrating with respect to y, from 0 to pi of sine y dy, you know that this one is readily integrable. The answer is negative cosine of y from 0 to pi. So let's bring out the negative sign. So it does not confuse us. Cosine of pi minus cosine of 0. Cosine of pi is negative 1. Cosine of 0 is 1. So negative 2. The answer is 2. So for this, the order is dx dy. So if u is 1 plus x to the 4, n equals negative 1, so dapat hopefully ln, right? So what's the du? The du is 4x cubed dx. We don't have an x cubed. So as it is, the order is not applicable. But if the order was dy dx, that means the whole thing underneath becomes constant. So we may be able to integrate this. So let's look at the limits. The limits are x equals y up until x equals 1. Y is 0 up until y equals 1. So let's draw this. X equals y is line. X equals 1 is another line. Y is 0, y is 1. So in here, even if I draw another line on top, you would know that we are, or we should be referring to the lower triangle, because from x equals y, which is this line, up to x equals 1. So we're sweeping to the right, not upwards. And then for the order, the square, let's decide where the square will go. Originally, it's dx dy. We would want it to be dy dx. So that means the square should travel up and down. So meaning the rectangle has to be an upright vertical rectangle. It has to be vertically simple. So this is dx. And then, sorry, that's dy. And then this is dx. So if we are to change the limits, guys, the problem will not change. It's just gonna change in order. But so let's look at the square. The square travels from below up to x equals y. But then now we would want the limits to be y equals 0 up to y equals x. And then travels from left to right. It starts from constant to constant. X is from x equals 0 up until x equals 1. It's this one. Now, let's integrate. It's with respect to y, meaning x is constant. So that means everything underneath can be brought outside. So that means this one is simply that problem. It's quite easy. So 1, x4, it's y from 0 to x. So this one is simply x, 1 plus x4. This is the answer for the first problem. Now, let's try to do the second portion, which is with respect to x. When we rewrite this, this becomes the integral from 0 to 1 of x over 1 plus x to the 4 dx. So as it is, when we look at it, let's try first ln. If it's ln, we need to have an x cube on top. But that's an x to the 4. What if, in here, what if it's arctan? If a equals 1, u can be x squared. The du is 2x dx. So that means all we need on top is 2x, right? So it's just 2. I can bring out a 1 half. And then integrating that, that's going to be 1 half times 1 over 1 arctangent of x squared over 1 coming from 0 up to 1. So 1 half arctan of x squared from 0 to 1. Let's bring out the 1 half. It's going to be arctangent of 1 minus arctangent of 0. This is pi over 4 minus 0. So all in all, you'll be able to get pi over 8 as your final answer. And that's the answer on top here. It's pi over 8.